find the probability of even A and if event A depends on some other event, I can use this law of total probability to find it as probability of even A condition on some other events times the probability of those events, right? Over N. But we have another law for conditional probability. Probability of A condition on some other, let me use the notation I have here. Yeah, for example, the probability of A condition on C. Now I want to write the law of total probability for a conditional probability. Here I have probability of A, but here probability of A condition on C. So this becomes handy for part B, I think, right? Yeah, for part B. So let's find this one. I want to write it in terms of summation of some probabilities. I know that based on Bayes formula, this is equal to probability of A and C over probability of C. Right? Bayes formula. Also, this is equal to probability summation of probability of A and C and some other events. I will explain probability of C. So, what is this notation? So, do you remember when you have joint probabilities by summing over one of the random variable, you can get rid of that random variable to find the marginal probability. Do you remember that? So this notation follows summing over one of the random variables in order to eliminate it, to get the marginal probability. This is equal to, and also I can write it here, probability of A n, C n, B n could be written as probability of A condition on B n and C times probability of B n and C. Do you agree? I look at this B and C together as one event and write the joint probability as conditional probability of A over this event times the probability of that event. Agree? Also, this part can be written as probability of Bn condition on C times probability of C. So I can simplify this term with this formula I wrote here. I can say this is equal to, so the numerator has a summation, you keep the summation. Now, instead of this term, I wrote the term I derived over the probability of A condition on Bn and C times probability of Bn condition on C times probability of C over probability of C. Now this probability of C is crossed out, and all I have is, let me check, yep, summation of probability of A condition on B and C. Let me check probability of B and condition. It seems correct. Probability of Bn condition on C. So you see from here, I wrote the law of total probability for the conditional probability. So these two terms shows up here, and I have probability of Bn condition on C. So it is a little bit different from the law of total probability I had before. Okay, part 1, question 1, part B. Question 4. for each possible value of k derived MAP estimate of the category that this student belongs to. So it's better if I go over the solution, so I use the same notation. We read it one more time. Suppose that randomly chosen answer k for each possible category. Okay, what we are looking for is I think I need this question. Hold on a second. Okay. So for each possible value of k derived MAP estimate of category of this student. Okay, so we are looking for the category of a student, knowing that the value of k was what? K, the number that the number of questions that are answered correctly. Okay. So what I'm looking for is probability of theta condition on k, and this is the distribution, theta condition on capital K. So again, these are the random variables, and these are what? These are some numbers. Based on base formula, this is equal to the probability of theta times probability of theta times probability of we change the place, k condition of theta over what I have to write here, because it has condition on k, is probability of k, right? What is k? K is the number of questions that are answered correctly, but it depends on the type of the student, right? So because this k depends on the type of a student, depends on theta, I need to replace this k by using the law of total probability. So instead of probability of k, I have to write summation of probability of k condition on theta times probability of theta. Make sense? So at the denominator, you always have what? Let me write it here. So at the denominator, always. These markers are not that good. Anyone has a marker, I can borrow. Well, here's something you do have. Thanks. Thank you. Okay. So at the denominator, always you have probability. No. Disappointing. So, oh, you have another one? The same. Okay, so at the denominator, always I have the probability of this conditional term. So, there's a point. If, for example, k is conditional on some continuous variable, for example, assume that theta is continuous, then instead of summation, you have integral, right? Then you have to do something like this with respect to theta, in order to find the probability of k, the conditional. So in case I have this discrete variable of theta, I have summation. Okay, now let's find each of the terms. What is probability of theta? Probability of theta, picking each of those students. each student is equally likely to belong to one of them. Okay, equally likely. So probability of theta is 1/3. Yeah. So now let's find probability of K condition on theta. Let's find this one. Probability of K condition on theta. So it means that now you know a specific student, what is the probability for that specific student to answer K correct, to give you K correct answers, okay? Probability of K condition on probability of K condition on okay, yes. So we have three types of a student. I know that if the student knows the answer, it will definitely answer the question. But otherwise, it will guess the answer correctly with probability of 1/3, right? Yes. So for example, a student, the probability of success, for example, PI, this is PI, right? It is, yeah, PI. So let me go over here. The conditional PI is binomial. Forget about this part. Find this PI. What is this PI? It's the probability that the student number I correctly answered the question, one question. So I know that with probability of theta I, he knows the answer and correctly find the answer, but with probability of 1 minus theta I, he doesn't know the answer, and then he will guess the answer with probability of 1/3. So PI is the probability that a student number I correctly find the answer. Does it make sense? So let me write it here. PI is what? PI 2 times theta I plus 1/3. So now I fix the type of a student. So I fix the type of a student. I want to see how many questions can he answer. This is binomial distribution, right? I have 10 questions actually, right? 10 questions. I have 10 questions. What is the probability that this student answered K questions correctly? Binomial distribution, right? Equal to K from 10 times this PI I found to the power of K, 1 minus PI to the power of 10 minus K. Correct? I don't have the solution. So the point was that I fixed the type of a student. Where is it? Yeah. I fixed the type of a student, and therefore I can find this probability because now I know the student. So I found this. What about the denominator? So again, the same term shows up here, probability of K condition on theta, which I found here. Now for each of these theta I need to write this probability and find the summation. But I really don't have to find this summation because of what? Because I am doing MAP. And for my MAP, for 3 types of a student, this denominator is constant, right? So, because for MAP, I want to find the maximum a posteriori. But for all of them, this term is constant, and also this P of theta is constant as well. So all I care about is this term. So the one that has a higher value of, larger value of K condition on theta I will have the higher posteriori. Make sense? Yeah, what is it? For a given number of category of binomial probability is maximized. Yes, we only care about the binomial probability. So because this term is constant. So for MAP questions, always this denominator is the same for all of the types of items you have. So you only care about these two terms. And most often, this term is also common. So MAP most of the time is simplified to likelihood. So you simply find the likelihood and you can find the maximum a posteriori. Make sense? Any questions? Clear? I think the second part is more challenging. Second part. Let M be the number of questions that the student knows how to answer. M be the number of questions that the student knows how to answer. Derive posterior PM and MAP and elements estimate of M given the student answer 5 questions. Yeah. Louder, louder, louder. Differentiate. Find the map. No, I don't think. Let M derive the posterior PMF. No, I don't think so. Is the solution differentiate? Question 6? No, that's different. Let M derive the number. No, I don't think so. Let me go over it. I think. Okay, so what is the, now, M be the number of questions that the student knows how to answer. Derive posterior PMF. Okay, I see. So what we are looking for is the posterior probability of M, the number of questions, knowing that the student answered 5 questions correctly. So this M is less than 5, right? Because he might have guessed some of the answers. That's the point. So X equal to 5, M should be less than 5, less than equal to 5. He might have guessed some of the answers. So now I have this posterior probability, but again, this posterior probability depends on type of students, right? Depends on theta. So I can use that law, the second law, law of total probability for conditional probability. Let me scroll down. No, I think, no, it's fine. Okay, so what I have here, after writing the conditional probability, I have, based on that formula over there, I have probability of M condition on this K and also the type of a student times another term that I wrote over there. Now we need to find each of these terms separately. For example, let's find this term. Probability of M condition on X equal to K, and I know the type of a student. Let's interpret it. Can you interpret it for me? We know the amount of success, okay? We know the type of the student as well. Knows, yeah. Okay. Knows how to answer, yeah. Okay. The questions that the student know how to answer. So what we can do, so I know I have K, which is what? Correct answer. Right. And also I know the type type of the student. So it's binomial distribution because then M out of K1s should be known by a student how to answer, right? Because at first I have to find the probability of, let's say, for example, PI. PI is what? Let's say it is the probability that a student knows the answer and he answered it quickly, correctly. Answered it correctly. The probability that. Okay, what is it? So, theta I is the probability that he knows the answer, and the probability that he answered it correctly is the probability that he knows the answer or he guessed the answer, right? This is PI. Right? So now I can find this probability with binomial distribution. I fix theta and the number of questions correctly answered out of how many questions? M questions with that probability. So probability of K condition on, M condition on K and theta is binomial distribution. M out of K1 with PI, parameters PI. Yes. Correct. Do we have solution? Binomial can be calculated in the, no. Does it make sense how I found it? Follow? So what about the other term? Probability of theta I condition on K. So we found it in the first part, I think, right? Probability of theta I condition on K, a posteriori in the first part. Theta condition on K, yeah. We found it here. Where is it? Yeah, so I found this part A, and also for this part I have binomial distribution. Now, what I'm looking for first is PMF. To find the PMF, you have to find different values for, you have to evaluate this function for different values of M. And I know because K is equal to 5, M could be at most equal to 5, right? Let me check the solution. Yeah. K could be at most equal to 5. So for each of these values, once you evaluate the function, you will get these probabilities. And they have to sum up to 1. Okay. Now, what is the next part? It asks about, okay, now we found the PMF, and we have to find MAP, maximum a posteriori. Okay, how can we find the maximum a posteriori? For each of these probabilities, I evaluated M, and I picked the largest one for the maximum a posteriori. So it follows MAP equal to M equal to 3, because this gives you the maximum one. So what's the meaning of this one? Let's interpret it. So 5 questions are correctly answered, right? So most likely the student knows only 3 of them, and 2 of them were just guessed. That's the interpretation, right? That's the meaning of MAP. This is most likely that 2 of the questions were randomly answered, and he was correct. Okay. What about least mean square we need to find expected value of, where is it? Yeah, expected value of m condition on x. Yeah, I think this part is straightforward. Where is the derivative you were talking about? It's for another question. We don't have derivative here. No.
Question 5.
Question 5. Any questions about this? This question 4 is very important. If you learn it, I think you'll be fine. So, I mean, you see, I just went over the questions. Some of them are really hard, so don't worry about it. But question 4 is like moderate. If you learn it, it's fine. Yeah. LMS, this means work. 1 point. Louder, please. LMS. Okay. You are right. The solution is not complete. But there is a point for your quiz. I think LMS is not covered, right? So let me skip this part. Yeah, you are right. It's not in the answer. Let me solve question 5 as well because I'm running out of time. Consider the variation of, question 5 is also important. So 4 and 5. If you don't have much time to go over all of the questions, it's only 4 and 5. Consider variation of bias point problem in the lecture slide and assume the probability of n distributed over 1 according to this P. Find the MA estimate of theta, assuming that n independent point constant result in k and n minus k from k. Yes. So for this question, we know that how many points lands on head, right? K of them. We want to say something about the probability of the bias coin being on head, landing on head, right? So that's the meaning of posterior. So you observe something, you want to make decision about the parameter of your distribution, underlying distribution. So again, you simplify it by base formula, but now the point is that in the denominator, here you have probability of k, but k depends on theta, and theta is a continuous random variable. So you have an integral to find the probability of k. But the good point is that, again, for maximum a posteriori, this term is constant for all of the different value of theta, right? So you don't have to evaluate this term if you want to find maximum a posteriori. Is that what we have to do, assuming that n independent of? Yeah. Okay. So here we have probability f of theta. F of theta is given, right? Now, what is this part? Probability of k head knowing the parameter of theta. Binomial distribution, right? Now, the parameter of your distribution is fixed, you are looking for k heads out of how many trials, n trials, yeah, n trials. Binary distribution, this term and this term. And this is the product. How do we know this is binomial? So we fix the parameter of theta. For example, I tell you, you have a coin, it lands on head with probability of 1 over 3. Okay. You throw the coin 10 times. What is the probability that you get 5 heads? What do you do? Binomial, right? 5 out of 10 with probability of, yeah. Makes sense? Because now we fix the value of theta. Now you can find the conditional distribution, which is what binomial distribution times the priority. Is the priority. Okay. Now we have it. Yeah, we have it here. Since the denominator is a positive constant, it is constant for all of the posterior distribution, so we don't care about it. What we have to do is to maximize the numerator, right? Because I'm looking for maximum a posterior. Now this is right. This is continuous. Because this is continuous, we have to differentiate it with respect to theta. We cannot evaluate it as single points. We have non-differentiable point here, right? Is that what we said? Yeah. At theta equal to 1 over 2, I have non-differentiable point. So what I can do is to first look at the points prior to non-differentiable point, then again look at this single non-differentiable point, and at the third time look at what comes after the non-differentiable point. I think this is this yeah. Yes. So does it make sense? Yeah. So we categorize it into 3 parts. So we evaluate it for theta equal to 1 over 2, and theta, for example, let us consider theta less than 1 over 2. Function we minimize ignoring the constant term. So we go to this one by equal to theta, provided that it is constant. Straightforward. Anyone has a question about this? Question number 4. No, 5, I think, right? Any questions about this? Nothing? Let's solve it up.
Professor, I have a question.
Yeah.
So can we, instead of dividing it into 3 segments, divide it into 2?
2?
2. I said, either theta is smaller or equals to half or larger than half.
No. 1 over 2 should be considered individually because it's non-differentiable point. It's an extreme point. No.
Okay.
You cannot include it in one of the intervals. No, that's wrong.
Okay, thank you very much.
Okay. One more question. Which question do you think I can solve? Question 8, you said? Probability of heads given point is known to be either Q0 or Q1. Because the point repeatedly and independently and record the number of heads before it's made up there. Assume that using heads and that are given prior probability and prior for part A and B, we also assume that probability of H1 is 0. Equal to 1 over 2. Calculate the probability that hypothesis station is true, given that there were exactly k heads before the first stage. that hypothesis H1 is true, given that there are exactly k heads before the first head. Okay. What we're looking for is the probability of hypothesis 1 condition on k. Hypothesis 1, meaning that the probability of heads is equal to Q1. Okay. So I use basic formula. I simplify it as probability of k condition on hypothesis 1 times probability of hypothesis 1 over probability of k. Probability of hypothesis 1. I see, we are equally likely. Yeah, I didn't see this. Okay, the probability of hypothesis 1 is 1 over 2. And what is the probability of k condition on H1? So you know that the coin lands on head with probability of Q1. And because you are looking for the first success, it is geometric distribution, right? You are looking for the first success. Yeah, here it is. We have geometric distribution for probability of number of trials before the first head. Does this geometric distribution make sense? No, it does not. It's fine. So I think numerator is fine. What is the denominator? Probability of k. Now for probability of k, again, based on the type of hypothesis, I have two possibilities. And each of them are geometric. I think the first part A is easy, right? What is the problem?
What distribution is it?
Geometric. Oh, let me explain. Oh, that's the part you have problem with? Read this part. We toss the coin repeatedly and independently and record the number of heads before heads is observed. Yeah.
So why isn't it binomial?
No. So the first one, all of the first ones are fail, and the kth one is success. This is the definition of geometric distribution. All of the first k minus 1 are failure, and at the end, at the kth one, you get success. Does it make sense now?
Yes.
That's why you have geometric series. Not series, distribution, sorry. Okay, if you decide, we go to the next part. Part B. Any questions about part A? Nothing? Okay, let's go to the next part. Consequently, decisions that decide in favor of hypothesis H1 if k is greater than some, and decide in favor of hypothesis H0 otherwise. Give a formula for the probability of error in terms of ECE2. Give a formula for the probability of error. Okay? For what value of k0 is the probability of error minimized? H1, I pick H1 if k is greater than k star. So when do we have error? If we pick H1 but k is less than k star, right? Where is it? Yes. I pick H1 but k is less than k star or otherwise. K is greater than k star and I pick H0. So this is the probability of error. Does it make sense? I think it is clear. Why do you say I solved question A? which part was hard? This problem with data summation. Okay, what else is part from K condition on H0? Start from K start up to infinity. So I have a summation of conditional probability. And for this one, K is less than K star. So starting from K0 up to K star minus 1. And I know that because this conditional probability is geometric, right? I found it here. What was the reason of geometric? Because I'm looking for the first success. The previous ones all were failure. And yeah, how can I find the summation? You know how to find the summation? Let me write some formula for the geometric series. I and A plus AQ plus A times Q to the power of 2 up to A times Q to the power of N is equal to, what was it? A times Q to the power of N minus 1, Q minus 1.
I think it's plus 1.
If N goes to infinity, A plus A times Q plus A times Q squared plus. This is equal to 1 over A over 1 minus Q for Q less than 1.
Professor, I thought the on the numerator it should be Qn plus 1, not Qn.
Q?
Qn plus 1. So the exponent should be n plus 1, I think.
The number of terms, because correct. Yeah. Is that what you said?
Yeah.
Yes, that's correct. Because I have n plus 1 terms. Yeah. Good. Yeah, so I have these two formulas. I use it to find the summation for the first one. Starting from K0 up to infinity. So let's match it with the formula I have here. I need to find the first term in my summation. First of all, take this out. 1 minus Q0, I take it out, I put it here. I have summation of Q0 to the power of K starting from K star. So A in this formula, A is Q star, right? A is Q star. And also, this Q is Q star. Yeah. Because the ratio is Q star. No, I mean Q0, sorry. So I have Q0 over 1 minus Q. Yeah, and for the second one, we just follow this formula. I think the remaining is straightforward, right? Now, what we're looking for is, for what value of K star is the probability of error minimized. So we need to find the derivative, right? Derivative of this error with respect to K. Where is it? Yeah. You know how to find the derivative of exponential? So here it is. I can prove it if you want. But it's fine, just memorize it. The exponent I have, again, K. So this term shows up and you can find it. What was part of this question? You were the one asking me to solve this, I think. No? You didn't get this question? So let me ask the class. So you guys, you don't understand this question?
I'm good. I'm fine.
You're fine? How about you?
I don't know.
Yeah.
So when we're doing part 3, is the PE, the probability of error, is it the conditional error squared error rate? Like,
I didn't understand. Sorry, what was it?
for the PE, B, P which stands for P.
Okay.
Is that error conditional? Like is the error always going to be conditional in this case?
Error is always conditional. No. What do you mean?
Aren't we basing on the hypothesis is equals to P0? The hypothesis is equals so H is equal to H0. So does that mean it's conditional or no?
Yeah, go on. Let me talk with you after the class.
Okay.
Any questions? Yeah, let me write it here.
So in fact, is the probability of something what's the when it comes to error?
Starting from summation, before summation time, before the summation. For example, for this one, do I agree that this term does not depend on k, so I can take it out of summation. So let's do it. Probability of h1 times 1 minus q0 times summation of k equal to k star up to infinity, k0 to the power of k, right? So let me write some of the terms for this summation. Let me write. So starting from k star, it is k0 to the power of k star plus k0 to the power of k star plus 1. Going to infinity, correct? Let's use this formula. It says the first term comes at the numerator. Let me write it. What is the first term? Q0 to the power of k over. What is the ratio? Ratio is the Q. Q like here. So here the ratio is Q. Q0. Yes, I think you got it. So you think you'll find this term as well? Any questions? Yeah.
Just generally, other than these questions 4 and 5, are there any other questions you'd recommend to go over for Friday?
4 is really good.
4 is really
Probability for probability, just review the probability. Also, we have questions from probability as well. So don't forget about that. So don't just concentrate on this main stuff. 3 questions. Yeah. You don't need to solve the hardest question in over 3. So I see that some of the questions they have long answers. I don't know what to. But yeah, so just some of the questions. Yeah, I think it's yeah, go
Give the exact copy of the problem. There will be some